Bumax is specializing in high-strength fasteners in different stainless steel materials. These fasteners can be found in applications in the most demanding environments all over the world. The quality and performance of our unique fastener solutions guarantee the lowest possible life cycle costs, as well as safety and reliability. Bumax has a long history and experience of stainless steel bolt manufacturing. Our products has developed over time, and we have become a world-leading developer and manufacturer of stainless steel fasteners. Today, Bumax is known for the strongest stainless steel bolt in the world, with fasteners manufactured from a wide range of stainless steel materials for use in the most demanding applications. Bumax help customers in various industries, crucially in applications where standard fasteners simply can't cope. Bumax stainless steel fasteners are a great alternative to standard stainless steel, carbon steel, and even sometimes titanium and nickel alloy fasteners due to their corrosion resistance and high strength, combined with the supreme fatigue properties. Our products are often used in marine and offshore critical applications with the need for extreme corrosion resistance, high strength, low weight, and a life expectancy up to 50 years. Fatigue and corrosion resistance are important in the pulp and paper industry, and Bumax products can ensure reliability and a long service life to ultimately reduce life cycle costs compared with standard solutions. This training course will take you through various topics that are relevant to Bumax, like corrosion, stainless steel materials, and how fasteners are produced. You will also get an overview of Bumax product range and the main features and benefits of Bumax products. A basic knowledge of these areas will help you to open up discussions with customers and identify possible situations and applications where Bumax could be of benefit. For more detailed customer discussions, you can always contact your Bumax colleagues for additional support.
Corrosion is a natural process that converts a refined metal into a more chemically stable oxide. It is the gradual destruction of materials, usually a metal, by a chemical or electromechanical reaction with their environment. Effect on the material can be very destructive, as the original material loses its strength and structure. Corrosion engineering is the field dedicated to controlling and preventing corrosion. Now let's take a look at some of the challenges that we face with corrosion. Corrosion costs the global economy over $2.5 trillion annually. That's a staggering 3% of global GDP. So the quest to develop technologies that address sustainability and cost is ever growing. Choosing the right fasteners play an important role in achieving these goals. Equally important though is understanding the different forms of corrosion, and this is something that we're going to cover now in the coming slides. Uniform corrosion, also known as general corrosion, is the uniform loss of metal over an entire surface. However, it is not the most serious form of corrosion of stainless steel because it is relatively easy to predict and see. This type of corrosion is perhaps the most well-known corrosion type in existence. A typical example would be red rust that you would see on metal that has been exposed to outdoor conditions. However, there are other types of corrosion that are much more serious, and they are pitting, crevice corrosion, galvanic or bimetallic corrosion, and stress corrosion cracking, otherwise known as SCC. And these are some of the topics that we're going to cover in the coming slides. Pitting corrosion is a form of localized corrosion which produces attacks in the form of spots or pits. Pitting corrosion may occur in stainless steels in neutral or acidic conditions. A typical example of this would be high chloride environments such as seawater. Pitting forms little pits on the surface of the steel, and this eats into the material. particularly destructive because it is not easy to assess the depth of corrosion attack that has taken place into the material. Crevice corrosion refers to the localized attack on a metal surface at or immediately adjacent to the gap or crevice between two joining surfaces. Crevice corrosion occurs at locations where oxygen cannot freely circulate, such as tight joints, under fastener heads, and in other circumstances where two pieces of metal are in close contact. Chloride salts, pollutants, and moisture from the environment accumulate in the crevice, which promotes corrosion. Some of the key points about crevice corrosion are: aggressive environment created within the gap, difficult for the metal to passivate due to lack of oxygen, and a mechanism similar to pitting corrosion. Galvanic corrosion, also commonly termed bimetallic corrosion, is an electromechanical process. That is to say, it occurs as a result of the flow of very small electric currents, usually between two dissimilar metals, which causes the more anodic of the two metals to corrode, the noble or cathodic metal being unaffected. A spectacular example of galvanic corrosion occurred in the Statue of Liberty when regular maintenance checks in the 1980s revealed that corrosion had taken place between the outer copper skin and the wrought iron support structure. Although the problem had been anticipated when the structure was being built by Gustav Eiffel in the 1880s, the insulation layer of shellac between the two metals had failed over time, and this resulted in the rusting of the iron supports. There are several different factors that can impact the type, extent, and rate of corrosion. For example, high humidity and high temperature environments will be more challenging. In addition, other external factors like pollutants in highly industrial areas, high salt content in marine environments, or acidic conditions that you could typically find in a chemical processing or food plant. Different materials will react in different ways towards certain factors. That's why it's very important to choose the correct material for specific conditions. To try and reduce the effects of corrosion, we need to give proper consideration to material selection. Considerations towards design factors that can ultimately help reduce corrosion. For example, minimize the number of gaps and joints in the assembly, and to avoid using lots of dissimilar metals, and to consider using a higher grade stainless steel that can help combat against the more challenging environments. Don't hesitate to get in touch with your Bumax contact for any further assistance, as we would be more than happy to help.